All right. Hello, everybody. This is Long Zhao um, from South Dakota School of Mines and Technology. In this presentation, what I want to talk about is I want to talk about impact of wildfire smoke on solar systems and power grid stability. So this is a little bit of background about this research. Back in 2020, September, we suffered a lot from wildfire smokes at that time. You can see during the wildfire happen around the Idaho or Yellowstone area, the smoke covers a lot of landmass. And even in South Dakota, this is where we are, you can see, and we had a couple days or very smoky. And at that time, I had a question, how wildfire smoke affect the solar systems? And those are two more pictures I want to show everybody. You can see during this very smoky days how bad it was. Okay, and this is a light smoky day, and this is severe heavy smoky days. You can see how bad it was back then. And those are two pictures we took on campus. Okay, um, so back then we found some information online. This is what we saw from KAISO website, and they saw that there's a correlation between PM 2.5 and the solar power output. They do see one, we have increasing PM 2.5 index, and the solar generation will decrease. That's what they saw back then. And I was trying to find some model like whether we can rely on PM 2.5 to predict, to quantify the wildfire smoke impact or not. But back then, I did not find any. So that's why me and my graduate student were trying to develop a model using PM 2.5. This is what we did. We bought different devices and we collected data on different days. But interestingly, you can see that during the smoky day, even the power has been reduced significantly. We lost almost half of the power, but AQI is still pretty good. That means the air quality is still good. But why? How come when we did see wildfire smoke on the sky, but meanwhile we lost ton of power from solar generation? Why the AQI or PM 2.5 is still considered good? So those are reasons. Well, it really depends on like what type of wildfire smoke you have, or like where you took the PM 2.5 data. For example, if you look at this, if you measure PM 2.5 around this area, well, you have the smoke, right? You have the smoke, and probably you will lose ton of power from solar generation, but air quality is still good. And but for here in this region, if you use PM 2.5, probably it will work. And another thing people have used a lot is called AOD, aerosol optical depth. But the one thing we cannot rely on AOD is that AOD only focuses on certain wavelength. And the reason we cannot do that is if you look at how solar cell works is different solar cell, they have different spectral response. What that means is for different spectral response, they will generate different power. For example, for first type, I'll say monosilicon solar cell, and you can see the effective spectral response is from like 300 to all the way to 1100 something. But for this blue dot line, you can see they have totally different spectral response. And that's why we cannot rely on AOD because AOD only considers certain wavelength. Normally it's from 500 to 550. And so the question is how we can model or how we can quantify the wildfire smoke on solar system in an accurate way. And also another picture I want to show is you can see during the smoky day, and this is sunshine, you saw probably the spectrum from the solar is from 600 to 700. With all this information, we just want to know how we can quantify the smoke impact on solar. And we came up with ideas called ARI, Absorption Radiation Index. And this is a spectrum-based quantification method. So how we can find ARI? ARI is defined as a amount of solar radiation affected by the suspended particles in the sky. And for example, there are two very extreme examples. The ARI is when ARI is equal to 0. That means a super clear sky. There's nothing in between. But when ARI is 1, means sky is fully covered by the particles. There is no sunlight. Okay. And with ARI, we can see how much solar irradiance will be blocked from solar to the ground or solar systems. And this is how we find CSS, PSS. Basically, we're trying to integrate irradiance from lambda 1 to lambda 2 for based on their spectral response. And with this, we're able to find ARI. Those are devices we need to calculate RI. We had a spectrometer and we attached this meter on the solar panel, so make sure we can have all synchronized data. So this is the results we got. And by the way, this is not a solar output. This is just a spectrum. Okay, this is a solar spectrum at 12 p.m. We picked 2 different days. The first day is super clear day, no smoke, no cloud. And the second day is there's no cloud, but we do only have smoke here. Okay, and you can clearly see the differences and how smoke change the intensity for different wavelength. And by calculating ARI, we found that the ARI and the solar reduction, they're kind of like a linear relation. And in addition, we also evaluated different factors, for example, temperature, humidity, wind speed, to see how important they are, like how much we can rely on ARI. So the result is that ARI is a very accurate way to quantify the wildfire smoke impact. And this is since the model we use calculate ARI is the solar panel we installed on campus, but to quantify, to use ARI for different solar cells, you have to consider a constant alpha-1 here. One thing I want to point out is you can see this for this type of solar cell, okay, the alpha-1 is only 94.7. What that means is if you do have wildfire smoke, and wildfire smoke will have the least impact on those type of solar cell. So this will give us a thought that if we want to install solar system in high risk wildfire areas, probably you should consider spectral response, because when you have different spectral response, so wildfire impact will have different, wildfire smoke will have different impact. And those are publications we had based on this work. The second part of this work is called a wiggle effect, and we're trying to understand how wiggle effect affect the stability of power systems. So where this work is coming from, during the smoky days, you can see that we saw some like zigzags on our solar output, and by that time we did not know what that was. And but just compare with this like super clear, non-smoky, cloudless days, you do see the power reduction here. But meanwhile, we also have the wiggle effect. We call this wiggle effect, zigzags. Okay. Initially, I thought there's something wrong, so we got another data source on campus and the solar irradiance, and we still saw the same thing happen. And after spending some time, we realized that this is all because of the smoke, because the smoke density is different. For example, if you look at this, right, this is a thicker, this is a thinner, and thicker and thinner again. That's why when you have a wildfire smoke cover, you will have a wiggle effect. Okay, so next is we're trying to quantify the wiggle effect, right? So how bad it can be. And based on the data we have, and based on the solar system we have, we realize that with 3 kilowatt solar system, we can have a 65 watts power deviation, which is around like 2.2%. Okay, and we just apply the same the wiggle effect to the larger system, because this we're just assuming this is the scalable. And by applying this in KISO and ERCOT, and this is how much we can find based on the 2.2%, we can estimate that power deviation caused by one wiggle effect could be like 577 for KISO, 224 for ERCOT. And based on power deviation, we will be able to find a delta F. Here is a frequency deviation. And this is the way we can find delta F, and based on the different frequency bias and in each system. So eventually we realized that with the 2.2% wiggle effect and the frequency deviation from each system could be like 0.116 for 0.16 for KISO and 0.02 for ERCOT, and compare with the standard or threshold that we call deadbands here, you can see this could be a problem in the future. And also to solve the wiggle effect problem, like we probably need a stable or fast response capacity. And how much would be that? How much is that? And so this is what based on the KAISO installed capacity, solar capacity back then in ERCOT. This is what we found. So the point I'm trying to make here is when you have more IVR installed in our system, that means we're going to have lower inertia, and meanwhile we're also going to have more solar installed, right? And we will have wiggle effect. And these two factors, combine them together, it could be a severe problem, serious problem. And we just put some numbers there, try to do a predictive analysis for each system. Let's say when we have a more IBRs installed, that means the beta is getting smaller with lower inertia, in other words. And we'll also have a more solar installed in different systems and see how bad can be. And this is based on the wiggle effect, and this is power deviation we can have in different year. And this is if we don't do anything, this is how much frequency deviation we could have in our systems. And this work has been published in these two papers. So the key takeaway from this presentation is that air quality cannot be utilized as an accurate way to quantify the impact of wildfire smokes on solar systems, because having said earlier, you can see how PM 2.5 value can be different based on where you are. And also the spectral response of a solar cell should be considered for wildfire smoke impact of the solar system on PV system. So because different solar cell, they have different spectral response. That's why the output could be different. Another thing is the wiggle effect should be considered as well for future power system, because when we have more solar installed, and especially when we have lower inertia, and with the more wildfire smoke, and the wiggle effect could be a serious problem. And so the point I'm trying to make in this presentation is I'm not saying the wiggle effect will happen or is happening right now. I'm just saying that based on what we saw, based on the observation, based on the data, based on our analysis, the wiggle effect should be considered in the future. Some of them, they brought one point is that when we have a larger scale solar systems, they could compensate, because it does not guarantee the wildfire smoke will only cover a certain area, but meanwhile they will not cover other parts of the region. It could be that could be one thing we need to consider, but at the end of the day, well, again, when we have more solar installed, lower inertia, more wildfires, and the wiggle effect should be something we need to consider as a power engineer or researchers in this area. All right, so with this, I'm gonna conclude my presentation. This is my email. If you have any questions or any comments you want to share, feel free to send me email. All right, thank you all for being here.